To understand the sound, we first have to understand two important aspects of it: frequency and amplitude. In this lesson, besides the definition, we will learn how it is possible to measure these two units. But before any measurement, we first need to understand the frequency. Imagine a hot summer day on the beach. You are enjoying the breeze while staring at the sea. You would probably see the waves hitting the shore repeatedly. If you use your watch and count the number of waves in a certain period, let's say 1 second for the sake of our example, you can measure the frequency of the waves that come towards the shore in 1 second. For example, 1 wave per second reaches the seaside. This example can also explain the frequency of sound waves. When we talk about the sound frequency, we talk about how often the pattern of high and low air pressure fluctuates in 1 second. We measure frequency in units of hertz, in its short form H and Z, which means cycle per second. But how do we perceive frequency? One may ask. We perceive frequency as pitch. The lower the frequency, the lower the pitch, and vice versa. Now that we learned what the frequency is, it would be a good idea to see some examples of it. The most simple frequency that we can generate is called sine wave. That's because it only contains one frequency at a time. Now, I would like to use my frequency generator to produce a particular frequency and use my digital oscilloscope to monitor that. When I set my generator on 1 Hz and turn it on, you will instantly see how does a complete cycle of frequency look. The x-axis represents the time, and y-axis shows the air pressure, which is also known as amplitude. We will talk about the amplitude in the next lesson, but for now, I would like to talk about the frequency cycle. One complete cycle of frequency, as you can see in our 1 Hz sine wave example, starts at 0, moves to 90, 180, and 270 degrees, and it returns to 0 once again. What you see is a complete cycle of 1 Hz. Some of you may notice that you cannot hear anything. That's because the frequency range that human ears can perceive at its best is between 10 Hz to 20 kHz. Now let's set our generator to produce 4 Hz. Look at the screen. We have 4 complete cycles, and if we go up within the human hearing range, you can also hear what you see. Now let me set the generator on 440 Hz. Look at that. Now we have 440 cycles on our screen. It is even hard to see, but let me ask you a question. Doesn't 440 Hz sound familiar to you? Yes, it is the standard tuning for the note A4, which many musicians use as an indicator to tune their instruments. If I add a tuner, you will see that the 440 Hz is the note A4. And if we double up the value and generate 880 Hz, we are moving up an octave to A5. It is how frequency and standard tuning links. Sound waves are mechanical waves, which means that they need a medium to travel from one point to another. If we take the air as an example, these waves move by vibrating the air particles. However, it is necessary to remember that the air is not moving anywhere, because if it does, due to lack of air, one could suffocate in front of a very loud speaker. The waves move by air particles vibrating and colliding with one another, going back and forth to transmit the energy from point A to B. It is also crucial to keep in mind that no matter how high or low the frequency, the speed of the sound is always the same. But how much is the speed of sound? As mentioned earlier, sound needs a medium to travel, and this medium can be different types of gases, liquids, or solids. However, the speed of sound varies based on the medium that it is traveling in. When the air has average humidity and temperature, sound will travel a little bit over 340 meters per second. In liquids, for example, in fresh water, sound can travel over 1,400 meters per second. And in solids, for example, steel, the speed of sound can reach over 5,000 meters per second. Remember, these numbers are just an example of their category, and the speed of sound even varies in different types of gases, liquids, and solids. In the real world, however, unlike sine waves, every musical note has a fundamental frequency combined with some additional frequencies which are known as harmonics. The combination of these two elements creates the timbre of an instrument. That's why one musical instrument sounds different from another. Although what explained earlier was the general definition of timbre, but to understand it better, we have to get more precise. Sound waves in the real world are mainly complex waveforms. It means that they are a combination of a fundamental frequency with other frequencies known as harmonics and overtones. When an object vibrates, it produces a combination of frequencies. The lowest of all is known as the fundamental frequency or first harmonic because it has the highest amplitude or loudness among the other frequencies and, consequently, it is the most audible, which provides the pitch reference. Otherwise stated, in any complex waveform, the fundamental frequency is the predominant among the rest. Along with fundamental frequency, a series of ascending sonic components will be produced above it, which are known as harmonics. The combination of these frequencies creates the harmonic spectrum of a sound. It is hard to distinguish harmonics individually as they have lower amplitude or loudness compared to the fundamental frequency. However, just like a painting that is a mixture of various colors, these frequencies together create a timbre of a sound source. The integer multiples of the fundamental frequency are the harmonics of that particular frequency. For example, if our fundamental frequency or first harmonic is 50 Hz, the second harmonic will be 100 Hz as the 50 multiplied 2 equals 100. The third harmonic will be 150 Hz as the 50 multiplied 3 equals 150. And the fourth harmonic is 200 Hz as the 50 multiplied 4 equals 200 and so on. On the other hand, overtones are generally referred to as any frequency above the fundamental which may not have any direct relation to it. If the harmonics are the integer multiples of fundamental, overtones are not necessarily related, and they are just higher frequency standing waves. Now we can define timbre in a more accurate explanation. The combination of the fundamental frequency, which is the pitch reference and has the highest loudness, besides harmonics, which are the integer multiples of the fundamental frequency, plus overtones, which are high frequency standing waves with no direct relation to the fundamental frequency, create the timbre of a sound source. This kind of waveform, unlike sine wave, is considered a complex waveform that we generally hear in the real world. Now let's look at some examples. This is a frequency spectrum visualizer that helps us to see the fundamental frequency and its harmonics in real time. For the sake of our example, each instrument will play the note A4 and we will be able to see the fundamental frequency which has the highest amplitude along with harmonics and overtones. Now let's begin. Even percussions are not an exception. Let's look at some examples. Lastly, it is interesting to see the differences between two different instruments playing the same piece of music. Here are the first few bars of Furelisa on piano and harpsichord. At this point in our lesson, it is good to look at the frequency range of conventional musical instruments. As we can see from the chart, each instrument lies in a different range of the spectrum. Simply put, this diagram shows the number of available octaves for each musical instrument. For example, if an instrument can play from A4 to A6, it can play from 440 Hz up to 1.76 kHz. As A4 equals to 440 Hz, A5 is the double of that value, 880 Hz, and, of course, A6 would be 2 times higher than A5, which equals to 1760 Hz or 1.76 kHz. In this picture, you can see the musical notes and their frequency equivalents. Having a good understanding of this figure can be very handy in music production, particularly when we talk about the function of the equalizer in later lessons. To summarize, frequency is the number of high and low pressure fluctuations in a certain period. The sound frequency, which is measured by Hertz, is the number of times that sound wave fluctuates in cycles per second. Sound is a mechanical wave, which means that it needs a medium such as air to travel. However, the particles of that medium are not going anywhere. They only vibrate and collide with each other to transfer the energy. And finally, we learned that our ears perceive frequency as pitch, and naturally, it has a direct relation with the musical notes as we know. For example, the standard tuning frequency for the note A4 equals to 440 Hz. So far, we learned about the fundamentals of frequency, and as you may expect, there are more aspects to it. A good sound engineer knows each frequency band perfectly, and when they work with audio, they know how and where to listen. Although acquiring such a skill requires a long period of ear training, but spending some time with equalizer can make you more familiar with this topic. But now, let's talk about the amplitude. The simplest way to define amplitude is how far sound fluctuates. Otherwise stated, how loud or quiet the sound is. With this explanation in mind, let's get back to our frequency generator to see the reaction of digital oscilloscope to the changes of amplitude. When I was explaining a complete cycle of frequency, I referred to y-axis as the indication of amplitude. It is because the louder our generator gets, the larger fluctuations will appear on the screen. I set the generator on 4 Hz and turned it on. If you look closely, the output level of our generator indicates 0. We will shortly talk about measuring amplitude, but for now, I would like you to think about 0 as the highest available output. As you can see, when I set the output level on 0, the fluctuations fill the screen. But as soon as it gets softer, the size of the waves decrease. Amplitude is the amount of air pressure that sound makes, and we use Pascal to measure it. Therefore, one can experience silence when the air pressure remains permanently constant. This table will help you to have a better grasp of Pascal unit. This chart demonstrates the amplitude of various environments and different types of machinery in Pascal. However, to have a better perception of loudness, we utilize the logarithmic scale. Accordingly, we use the unit of decibels to measure sound level. But interestingly enough, decibels is not a unit of measurement at all. Instead, it is only a ratio of comparison. As the result, to use the decibels as our unit, we should have a reference point to start. If we assign the 0 decibels to the threshold of hearing, due to its logarithmic nature, we get these numbers to include in our table. We mark acoustic sound pressure with SPL, which stands for sound pressure level. Everything we learned about frequency and amplitude is summarized in this figure. You can see high and low frequencies with various amplitudes. I highly encourage you that before moving any further, take your time and understand the concept of this table entirely. As the last word of this lesson, I would like to emphasize that this course is not about how fast you can learn. Instead, it would be very constructive for your future career if you take fundamental information here and do your research elsewhere. So I will see you in the next lesson, where we talk more about frequency and we will learn about our hearing organ.